Recording in progress.
Hi, Professor Elias. Good morning.
Good morning, everyone.
Can you write that all on the iPad?
Yeah.
Yeah.
My iPad is like 8%. But yeah.
No, yeah, I got you.
And you have password too.
Yeah, I got you.
You have C's on here.
Type C, I don't carry it. I got back and forth.
Is there someone who has some C-type charger?
Bigger.
No, I don't.
C-type.
Is that like a Mac or whatever?
No, Samsung.
Oh, no, sorry.
You don't.
My bad.
It's okay.
Maybe the tutoring?
Maybe, yeah.
I don't know.
That's true. We're right by one of those writing centers.
Okay, we start. Any questions? Okay. Before I start the material, I would like to make a comment about the quiz. So the comment is about number 2, which was an occurring mistake.
Increase the volume.
Increase the volume.
Make sure the audio is on.
Yeah, mute yourself.
Okay. So the question was, I gave you the curve in the second.
Oh, it's just quiet.
Okay, I have to. So the problem was, I gave you the following curve.
Like
y squared minus y and x equal to 0. And quadrant 2. Okay. And the question was to find the area. So the graph was, most of you drew the graph correctly. Most of you. X equal y squared minus y. I told you, you guys remember how you would draw y equal x squared minus x. So if you draw y equal x squared minus x, you know that it's a parabola. And if you look for the zeros, you zeros at once. So this is y equal x squared minus x. This is basically the same thing, but the axis of symmetry is parallel to the y-axis, the x-axis. So if you draw this, you know it's going to be a parabola going this way. To have it exactly, you find the zeros. So y squared minus y equal to 0. Y times y minus 1 equal to 0. Y is 0 and y is 1. So the zeros are here. 1. And this is this parabola. Okay. And x equal to 0 is the y-axis, and I told you the second quadrant, it means this is the region we're interested in. Okay. Now, what is the area? As usual, here, because x is already given as a function of y, so we definitely want y to be the variable. X as a variable is problematic here, because if you want x the variable, you have to solve for y in terms of x, and which is already complicated, and the region tells me it's wrong. So y is my variable here. Okay, so basically I need to draw a very typical rectangle and find the area of this rectangle and then add the sum of the area of all those rectangles that cover the region. And now this is the question here. Suppose I call this y or yi. I don't really care which letter you use here. So y, it means from here to here I have y. That's the picture in my mind. So the question is, what's the length from here to here? And that's where the mistake happened. What's the length of this line segment? I tell you what a lot of you said, and then I will tell you that it's wrong. Most of you told me, so this is 0, this is the curve, x equal y squared minus y. means the length is y squared minus y. And that's wrong. For first reason, y is negative here. Sorry, y is positive. If you plug in a value of y here, this from here to here, that's a negative number. So if you give me y squared minus y, this is actually going to be negative number, which is not be the length. The length is always the right value minus the left value. So it's going to be always 0 minus y squared minus y. So it's the right value, which is a 0 here, minus y squared minus y. Very simple example with numbers. Suppose this is from here to here. Suppose this point is, I'm just making up stuff, 2, sorry. Suppose this point is minus 4, 2. Means this is the 2. The point here is negative, means from here to here is minus 4. So what's going to be the length of this segment? It's not going to be minus 4, that's for sure. It's going to be basically minus 4, or 0, which is the right value, minus the left value is going to be 4. So when you guys put y squared minus y, you ended up with a negative area, and you then by magic you made it positive. That's wrong. The length is 0, the right value, minus y squared minus y. So that was the mistake of a lot of students. And with this in mind, the area is going to be the integral from 0 to 1 of 0, the right value, minus the left value dy. And with this setup, you actually get the positive number 1/6. For those who got negative number, you got it because you cannot make negative positive by magic because the setup was wrong. Are you with me on that? Question? Okay. Let me, before I move on, let me ask you a fairly similar problem. And you guys, I want your answer. Suppose I give you the following picture. Okay, just I'm making up a picture. And suppose I give you the following picture. So I take a function, and now suppose I take something like that. Okay, this is the graph of y equal, let us say, x squared minus 4. So now I'm working with x as the variable. So this is minus 4. This is a 2. And let us say this is a 6. And I'm interested in the area of the shaded area. Okay. So question, is this true or false? Because this we have basically the same. The area is the integral from 0 to 6 of x squared minus 4 dx. True or false?
And I thought it was false.
This will be absolutely false. This is absolutely a false statement. How would you find the area? Remember, the area is the integral is the signed area, it's not actually the area. So how would you find the area of this region? Anybody, please speak up. 0 minus, Aaron, 0 minus, that's half of the story. Be more precise. This is from where to where? And do I need to split?
No.
It's 0 to 2.
We have to split. Absolutely. From 0 to 2, we have one scenario totally. And from 2 to 6 is a very different scenario. The function is negative and the function is positive. Very, very different scenario. From 0 to 2, the area is like the problem we had here. Like number 2, but I'm doing the same thing where x is the variable. If you take your rectangle here, the length is going to be the upper value, which is a 0, minus the lower value. So up to 0 from 2 is going to be the upper minus the lower. The function is negative. If I put x squared minus 4, if this is x from here to here, if I plug in a value of x into the equation, like I plug in 1 here, I'll get a negative number. The length has to be positive. And then from 2 to 6, which is right here, I don't have an issue. That's a positive function, and the length is going to be the upper value minus the lower value, which is 0. Okay, so we have to be very, very careful when the functions start taking negative value. We don't take the value of the function, it's the upper, which is 0, minus x squared minus 4. Okay, any question about that? So that's the mistake that stood out. The rest was, each student was different, and you guys have the comments on it. So today we are going to take the problem that I mentioned last time at the end of the hour on Friday. And before we start doing the work, I remind you what we are about to do. We still were working with volume of revolution. And last time we took the following type of region, a region like this, and we rotated it. That's what we did. And we got that. And the way we found the volume, we say, okay, we are going to cover this with thin rectangle, and we rotate each one of them. By doing this, we're covering the main region with cylinders, and we're adding the volume of the cylinder. And then the idea was that if you take this and you rotate it, basically you're getting an honest-to-goodness cylinder. We found the volume of this little disk, we called it, and we added the volume, giving me the volume of the whole region. Today's section, and not the same section actually, the idea was instead of rotating one curve, we're going to rotate a region between two curves. That's the idea. And it's the same logic we are going to use, but this time when I rotate every piece, I have a big hole here because I'm rotating around the x-axis. So when I'm rotating, I'm getting a disk, and as you guys said, with definitely a hole inside, which we are going to call the washer. And the question is, how are we going to proceed in this situation? So that's what we are going to do today. It's not hard once you understand the geometry. So first, the volume of revolution, the washer's method. Oops, sorry. Volume of revolution, the washer's method. Okay, so before we start doing the math, let us see what is a washer for us. Let us define the washer. The washer is nothing more than a disk. So imagine a quarter that you put a hole in it. A disk with a hole. That's really what the washer is for us. And let's see what's the volume of the washer. So I'm going to draw it a little bit here. And together we're going to find the volume of it. So it is this disk. So we have that. And then there is this hole in it. So this is really my washer. Okay, so that's the washer. And from here to here, that's the height, which is going to be either the delta x or the delta y. So that's really going to be the height. So what's the volume of the washer? What do we need to find the volume of this washer? What do you think? And that's the center. This is where the axis of rotation is really going to be. What do you think we need to find the volume of this washer? What information do you think you need? Ideas? How would you find the volume of this washer? volume of the disk minus the volume of the hole. Exactly. So volume of disk minus volume of the hole. Okay, very good. To find the volume of the disk, we definitely need the the radius of the disk. From here to here, that's the radius of the disk. So we are going to call this R0, and this stands for outer radius. That's the outer radius. And then, so the volume of the disk is going to be pi times the outer radius squared. That's times the height, which is going to be the delta x minus the delta y. I'm going to take away from it the volume of the hole. To get the volume of the hole, so I need the inner radius, so this one in red, we're going to call it Ri. I stand for inner radius. That's the inner radius. So the volume is pi times the inner radius squared times the height. Okay, that's exactly what you guys said. Now we're going to factor out some things. The height for both of them is the same for the disk and for the hole. So I'm going to factor it out. And I'm going to factor out the pi as well, just to make the writing easy. So this will give me the following. So I'm factoring those out. And what I will be left inside is the radius, outer radius squared minus the inner radius squared. So the volume of the washer is going to be that. Now let me a little bit connect it one more to the following idea. Questions about this. And that's about the only thing I wanted to memorize from that. There is no formula whatsoever. Once we know this, as you will see in a minute, we will solve every problem we need. So, but let me comment a little bit about this piece here. This is the height. Let me comment about this first piece. I will call this here, we're going to call this the base of the washer. Base of the washer. So I can draw here, right there, the base. So right there. So this is the base. I drew it here. Okay. And I mean, of course, this is the base. That's the inner here, and that's the outer. This piece right there actually represents the area of the base, because what's the area of the base? It's pi times the outer radius square minus pi times the inner radius square. So the area of the base is exactly that. It's pi times the outer square minus pi the inner square, because the area of the big circle minus the area of the small. So it means pi times R0 square minus that square. So this piece here actually represents area of the base. Okay, so area of the base times this little height gave me the volume of the washer. So it's a good way to think about it as well. So the volume of the washer is given by this formula, and the way to can better analyze it is the area of this little piece times the little height. Okay, so that's really a washer. Now the same thing will go if my washer is actually horizontal like this. So it's the same story. Okay, the same for horizontal washer. The only difference that in this scenario, this is going to be the delta y. In that scenario, the height will be the delta x. All right, so now let us see. As I said, I will not give you any formulas. That's the only thing you guys will ever memorize for the washer's method. The rest is you will figure it out with the problem. So let's see what the problem is, what's going to be our strategy, and then we do a bunch of examples. So this is the problem. problem is the following. So we have R is a region bounded by two curves equal g of x, x equal a, x equal to b. So it's just a curve. As the solid obtained by rotating R about the x-axis. The question is, find the volume. As I said, no formulas, but this is the way we are going to do it. All right, so this is my region here. And this is the region rotated. So something like that. Okay, that's my region R. I'm gonna rotate. And when I rotate is we get that. Promise you I will not do a lot of those, but something like this. So this is the curve down here, and this is gonna be the straight line. Okay, so that's what's happening in here. My axis of rotation is that. So the way we are going to do it is like this. So first, cover R with thin rectangle. Okay, that's our principle. So we're gonna cover this with those little pieces. So this is my xi. Okay, we're gonna rotate each rectangle. And this will give me a washer. Because when I rotate this rectangle, there is a big hole in here, I get a washer. So basically, this is my picture here, and this is where my washer are gonna be. And I have not great drawing skills. So these are the washers. Okay, and the idea is we're gonna cover the solid. This solid, we will cover it with washers. So you can imagine this solid is just a washer next to a washer next to a washer. So it's like you can imagine the inside is a bunch of washers next to each other. And that's how we're going to approximate it. So approximate as the volume with sum of volumes of washer. And finally, set up the integral. Okay, that's the way we are going to do all those problems. So no formulas, we're going to do examples and you will figure out the formula every. But that's really our approach. We are going to cut this into a little rectangle. We rotate each. By doing this, we are covering this solid with a bunch of washers. We find the volume of each one of them and then we add it. So examples. Let's start with examples. So example number 1. And now I want you to be careful and I will be asking you always question. What's the inner circle radius? What's the outer radius? So example number 1. I'm going to take R to be the region bounded by y equal square root of x, y equal x squared. Okay. Find the volume obtained by rotating R about the x-axis. Find volume of solid obtained by rotating r or revolving r about the x-axis. Step number 1, as always, has to be sketching the region. So we're going to sketch the region. Okay. Y equal root x. All of you know it by now. Y equal x squared. So this is y equal square root of x. And this is y equal x squared. The axis of rotation is the x-axis. So we're going to rotate this. And we got some kind of a region, something like that. That's the rotation. Okay, as you realize, it's a big, if you can say it like a big ball, you're taking it away like a cone-shaped object. So that's really the rotation. And now we're going to do step by step. We're going to take a slice, this little piece here. This is my little, and I'm going to call this right here. You can call it X, you can call it XI. It doesn't really matter to me. So this is my little XI. So the idea is I'm going to fill this with those rectangle and rotate each one of them. Now, when I rotate this, I will never rotate on this picture. This is for labeling. I will do rotation here. So I will never encumber this. This I'm going to use it to explain everything. So I'm going to rotate this. When I rotate that, that's my axis of rotation. That's going to be, that's the picture we're going to get. Okay. All right, so that's the washer. That's a typical washer. Okay, I need to find the volume of a typical washer. So let us analyze a typical washer. To be able to find the volume of a typical washer, I need the following. I need the outer radius, I need the inner radius, and then I apply the formula. That's really what it is. So what is the outer radius? What's the inner radius? What is the height? And finally, the volume. So this is a typical washer. Now we go back to the picture. This is the piece that I need to rotate. So what is the inner radius? The inner radius is going to be the distance from the axis of rotation all the way to here. You just look at the picture and figure it out. This would be my inner radius. So it's going to be what, my inner radius? If this is xi, this is the curve y equal xi squared, the inner radius is going to be xi squared. That's the inner radius. Now what's going to be the outer radius? That's the axis of rotation. The outer radius is going to be from the axis of rotation from here all the way to here. That's going to be the outer radius up to here. So from the axis of rotation to the curve, which is farther away from the axis of rotation. That would be my outer radius. So if this is xi, this is going to be the square root of xi. So my outer radius is going to be the square root of xi. So now basically this will allow me to find the area of the base. Now I'm going to multiply it by the little height, which is in my scenario, my little delta x right here. So the volume of the washer is going to be pi times. That's the height. And that's the area of the base. This is equal to the outer radius square minus, you're not taking away the outer minus the inner. You're taking the outer square, this takes care of the area of the big circle, and you're taking away from it that. So now we substitute everything. So this is going to be pi times. The outer radius is the square root of xi squared minus the inner is xi squared. And practically we are almost done. So you don't need, as I said, to memorize anything except the volume of the washer that we can almost figure it out easily. So the volume of the solid is almost equal to, at this stage, I'm imagining my solid totally filled with those washers, and I'm adding their volume. It's the sum of the volume of those. And finally, I will turn this, I see in that a typical Riemann sum. So the volume is going to be the integral. I'm going to add those. And I'm still not simplifying. I will simplify at the end. I'm keep trying to remind you, outer minus the inner square. And again, we go back here to find the limit of integration. I go back to my region and I need ask myself, what should I split into pieces to cover the whole region? So I go back here and I realize that I did not find my intersection point. That's the point I need. So let us find the intersection point. I should have done it before. So I will set square root of x equal x squared. I know it's very easy. I know that you can just look at it. But some of you had difficulty solving this equation on the quiz, so I will just go ahead and do it. Because I have the square root of x, the only way you solve, you have to square both terms. So square both terms. And that will give me x equal x squared squared x4. So that's how you solve this. And then you set this x squared minus x equal to 0. You factor out. And then you get x equal to 0, x cubed equal to 1, giving you x equal to 1. So this point is going to be 1, 1. So this is right here, 1. So finally, this is equal to integral from 0 to 1 of that. And now the rest is actually trivial. Sorry, I did a mistake here. That should be x squared squared. So finally, this is the integral from 0 to 1 of pi. Square root of x squared is x. X squared squared, you multiply the power x4 dx. And there is nothing left here. That's a fairly simple integral. A half x squared minus a fifth x5 between 0 and 1. Pi times a half minus a fifth minus a 0, because at the lower limit. So you get 5 minus 2, 3 pi over 10. Okay. Please ask any questions you have. Very good. So we're going to do one more example along those lines, and then I'll change a little bit the axis of rotation. So example number 2, and this time you give me the outer and you give me the inner. So this time R is the region bounded. R is the region bounded by y equal x squared plus 1. Y equal to 3. And x equal to 0. And I want it only in quadrant 1. Okay, rotate R about the x-axis and find the region. Find the volume. Step number 1, always graph. As you realize, there is nothing I can do without graphing. So let us graph the function. Y equal x squared plus 1. Since I'm only interested in the first quadrant, y equal x squared plus 1 go like this. So that's the y equal x squared plus 1. That's the axis of rotation. Y equal to 3, so this should be a 1. This is 3, so that's y equal to 3. X equal to 0. So this is the region I am rotating. Okay, so we're gonna rotate that here. Okay, you don't always have to draw the rotation, it's really up to you. So we're gonna get something like that. So basically it's a cylinder, you're taking a ball away from it. All right, so we're going to do exactly the same thing. I'm gonna take a piece here, an arbitrary piece, and xi. But before we do any of this, I need to find the intersection point. Okay, how can I find the intersection point? Quickly. What's the intersection point? You can give me the intersection point. I know it's Monday, but you guys can still awake. If intersection, set the bound equal to each other. Tell me what the bounds are. Luke, tell me what the bounds are. X squared plus 1 and y equal to 3. Exactly. So it's going to give me x squared equal to 2. X is plus or minus, but I'm only interested in the positive one. So the point right here, this is the square root of 2. All right, so the picture now, the graph is complete. Now we have to focus on that. So we're going to rotate this piece and we get this washer. And now my goal is what's the inner and what's the outer. And this is where at this time you guys have to give me all the answers. So typical washer. I'm finding the volume of one of them and then I'm going to add them. So what characterizes the washer is the inner, the outer. Let's give me area of the base, the height, which give it as a volume, and then finally the volume. All right. What is the outer radius? The picture is in front of you. What is the outer radius? Outer radius is 3, absolutely correct. This is my xi. When I'm rotating this, it's from the axis of rotation all the way to the outer curve, from here to here. That's the outer. So the outer is 3 in this scenario. What is the inner? From the axis of rotation to this curve, because when you're rotating, that's going to be from here to here. This is the inner, which is nothing more than whatever the function take at xi. It's xi squared plus 1. That's the area of the base. We got the inner, the outer gave us the area of the base. And then I multiply by the delta x, which now gives me the volume of the washer. So delta x make it into a volume. Otherwise, I only have an area. So the volume of a typical washer is pi times area of the base, which is the outer square. So that's the outer square minus the inner square. So that's the area of the base of the washer. Now the delta x will make it into a volume. Now I have the volume of the washer. We're done. As far as I'm concerned, we're done. The volume of the solid is, I'm skipping the Riemann sum, is we add those little things. We add the washer of those little ones. So it's going to be pi times 3 squared minus x squared plus 1 squared. And the limit, crucial, always the limit. To cover the region, x has to we have to divide the interval from 0 all the way to square root of 2. And now the rest is evaluation of this integral. So that's the integral from 0 to square root of 2. Pi is a constant. I take it out. Now I have to evaluate this. This is 9. This piece, the only way, there is one way to evaluate this, we have to expand it. Otherwise, or distribute. Otherwise, I cannot evaluate that. It's not substitution because the derivative of the inside is not outside, so we just have to distribute. So this would give me x to the power 4 plus 2x squared plus 1. And now I think the rest is simple, so it's equal to 0, square root of 2 of, that's a pi, 9 minus x4 minus 2x squared minus 1 dx. It means pi times the following integral. Now, if we can simplify the inside, we do. Otherwise, we start integrating. But I see 9 minus 1, which give me an 8 minus that. And finally, I'll get the following. I will not evaluate. I'll leave it to you. It's not very hard. 8x, antiderivative of 8, 1 over 5th x fifth minus 2/3 x cubed equal, you guys finish it. Okay. Questions? You guys very quiet. All right. Example number 3. I'm going to do, in a way, the same idea, but instead of rotating about the x-axis, I'm going to rotate about an axis parallel to the x-axis, a little bit below it or a little bit above it. So this is my setup. So example number 3. The region is the same, so we're going to rotate the R, region bounded by the region as in example 2. So I'm not gonna change the region. But now I'm going to rotate R about, not the x-axis, about the line y equal -1. So that will be my first question. Question is, find the volume of the solid obtained. The principle is the same, nothing changes. I mean, everything is the same. There is a little bit of a change in the scenario. So my graph is, as I said, I did not change the previous region. So this is x squared plus 1. This was the intersection point, which was square root of 2 and the 3. So this is my 3, and this is my 1. The only main difference is my axis of rotation is the line y equal to -1. So that's going to go down here. This is -1. This is my axis of rotation. So I'm not rotating about the x-axis. I'm rotating around that axis. But the idea is the same. I cannot really change the idea. The idea is really verbatim the same. I'm going to take a piece here. I'm going to rotate it about that. So in a way, the hole inside is going to get larger compared to the rotation about the x-axis. We're going to make the hole inside a little bit larger. So this is my little piece, and this is my xi. And this is my axis of rotation. Okay. So when I rotate this, remember, that's the axis of rotation. I'm rotating around that. So the holes are becoming the hole becoming bigger. The radiuses are actually changing as well. So now let us find everything. Question number 1 is typical washer. What's the outer? What's the inner? What's the height? And finally, the volume. So I go back to my picture and I said no memory except volume of a washer. So that's, we're rotating now around that axis here. So when I'm gonna rotate this piece, that's the center of rotation right there. So this is gonna go like this. And from here to here, it's gonna go all the way down. So a little bit different. Now I go back to you. What's the outer radius? And what's the inner radius? Before I draw it, I want answers. What's the outer radius? Let us fixate on that. The outer. Yeah. Try to think about it and put answers for me. No, I don't. I disagree. If the answer is 3, I disagree. Look at the picture. Right. Anybody else? Look at the picture. Don't memorize. Look at the picture. I will label it in a second, but I want you to interact with it first. Anybody agree with Jonah? Okay, let's see where he got his four from. This is the axis of rotation. It's right there. We're rotating about this axis. So what's going to be the outer radius? The outer radius is going to be from the axis of rotation, which is sitting all the way here, up to this curve. It's going to be from the axis of rotation up to this curve, because that's the center this time. So I'm going to rotate all the way down to here. So that's really is going to be my apology, my outer radius. It means that's the center of rotation. So I'm going to go from here all the way down to here. So the outer is going to be from the axis of rotation till the outer curve. So this from here to here, I will mark it one more time. This is the outer, which is going to be 3. From here to here, 3, you add 1. Equal to 4. Or you can say it's the upper value minus the lower value, which is minus 1, which is equal to 4. Okay, so the outer radius that's the axis of rotation this time. So the big, so the outer circle is much bigger. The radius for the outer circle is way bigger than when we rotate it about the x-axis. So the outer is going to be absolutely 4. Now I want you to think a little bit about the inner radius. What's going to be the inner radius? Look at the picture in front of you and think geometrically. What's going to be the inner radius? X squared. Keep thinking. Draw the picture and keep thinking. First, label it from where to where. It's going to be, that's the axis of rotation. That's the bottom curve. The inner is going to be from the axis of rotation. That's going to be the inner. Okay? Yes, Josh is correct. So what's going to be the inner? All right, if this is xi here, this point here, this is xi squared plus 1. So this is xi squared plus 1, but what you're going to do to it, you're going to add the 1. So the inner is going to be from here all the way to here. So from here to here, you have 1, if you want to think geometrically. And from here to here, you have x squared plus 1. So it's going to be xi squared plus 1, and you're adding 1 from there. So it's going to be xi squared plus 2. So the inner radius is going to be geometrically xi squared plus 1, and you add 1 to it. Or another way you can say the inner radius is going to be equal to the upper value, which is xi squared plus 1, minus the lower value, which is minus 1. It means it's going to be si squared plus 1 plus 1. It means the distance, the vertical distance from the axis of rotation to the curve, but you're adding 1 because you are basically increasing this radius. So it's going to be xi squared plus 1 minus 1. It means xi squared plus 2. So that's the inner radius. Everything is bigger. The outer is increased by 1 and the inner is increased by 1 because we're changing the axis of rotation. My height is the delta x. And finally, my volume. So this is the area of the base of the washer. You're multiplying by the delta x to capture a volume. So this is going to be the outer radius square minus the inner radius square. That's the volume of the washer. Now the total volume is the integral from 0 to square root of 2 of pi times the outer square minus the inner square. And this is the little height, plus 2. And finally, you just evaluate. Pi is a constant. We take it out. And inside, I will have 16 minus. As I said for the previous one, the only way you can integrate this is if you distribute. And that would give me x to the 4 plus 2 times 2, 4x squared plus 4. So finally, I will have pi integral from 0 to square root of 2 of 16 minus 4, it's a 12, minus x to the 4 minus 4 x squared dx. And the rest is actually a simple integral that you guys can evaluate easily. I will have 12x minus 1/5 x5 minus 4/3 x cubed equal, we plug in the upper minus the lower. Okay. All right, so I want you to go back to this example by yourself, see if you try to understand it, and of course the previous one, and please do the homework for tomorrow. I don't want you to memorize any formula. There is only one formula I want you to memorize in this whole thing, which is the volume of the washers. That's it for one washer. If you know this formula, the rest you should be able to figure it out from the graph. Do not memorize anything. Any questions? Okay, please do the homework for tomorrow. And as you guys know, I have office hours now from 12 to 1. So if you guys have any question, don't shy away from showing up. Any questions before I let you go? Okay, so bye-bye for today, and I'll see you tomorrow with questions. Bye, guys.